think it's definitely the distance. I think it's the distance, maybe.
Okay. Okay, so welcome everyone to the Cryosphere Pavilion at COP30. My name is Gustav Hegelius from Stockholm University and the Bolin Center for Climate Research. And today we are starting Permafrost Day. So we have the first of two sessions. Now we're going to have about 1 hour, and then 2 hours later after that we have our second session. So to start us off, this first session, we have Professor Hugues Lantouille from the Alfred Wegener Institute, who's going to give us a nice introduction and overview talk on the topic of permafrost and how it is affected by climate change. So please, Hugues.
Thank you very much, Gustav. It's a pleasure to be here, and for our listeners that are online, I must explain that we are forced to wear those headsets here so that people can actually, we can hear each other because the whole setup at the COP is actually very, very noisy. There are presentations everywhere around here. So, permafrost is warming fast, but before I make that statement, I need to explain what permafrost is. And permafrost really is what you see behind me. It's frozen ground. Actually, frozen ground is not a specific material. It's meant to be a thermal condition of the ground. It's ground that remains frozen for 2 summers in a row. And that's really what you see here behind me on that picture that was taken in northwest Canada. It's a massive amount of sediment that is frozen and that is intertwined with ice. And that ice is holding the whole material together. What is very special about the permafrost is that it contains a lot of carbon. In the atmosphere, you see we currently have about 880 gigatons, but in permafrost we have in excess of 1,500 gigatons here that could be released if temperatures continue to rise. But we'll hear more about that from Fabian later on during his presentation. Now, permafrost is very widespread, and it's very widespread in the northern hemisphere. Here you see that it covers large parts of areas of the Arctic, in Asia, in Europe, in North America, but also that is located under the sea. Those are the dashed lines that you see here on that map here, like very large parts of the shelves of Siberia are underlain by permafrost. And permafrost is not only in the Arctic, it's actually not very far from here in Belém. In Belém it's actually really hot right now, but if you'd go a bit west toward the Andes, you'd find some permafrost. There is permafrost here in the Arctic, there is permafrost, extensive permafrost areas in the Tibet Plateau here in Asia. And if you look toward the southern hemispheres here, you have like the entire Andes that are underlain by permafrost, and of course the unglaciated part of Antarctica. Now, one thing that is important about permafrost is that permafrost thaws and it doesn't melt. And the best analogy for that is a chicken. If you take a chicken, you put it in a freezer, and you take it out, that chicken is not going to melt unless it's a very special type of chicken. If you put ice or water in a freezer, it's going to freeze, and when you're going to take it out, it's going to melt. So in permafrost, ice melts, but the permafrost itself thaws. Why we're making that distinction is that it has very important implications, for instance, for engineering and for houses, buildings built on permafrost. How do we know that permafrost is warming, which was the title of my presentation? We know that because we have a worldwide network of measuring stations that are recording permafrost temperatures and permafrost active layer depth. The active layer is really like the thin part of the permafrost on top of the permafrost that thaws during the summer and refreezes during the winter. Underneath you have permafrost, and basically what we do through this network called the Global Terrestrial Network for Permafrost, we go on the ground and we measure permafrost temperature. That network is part of the overarching network of observations that is managed by the GCOS, the Global Climate Observing System, and that contains a lot of what are called essential climate variables. And permafrost is one of them. It's located here. It's called the Permafrost ECV. And there, through that ECV, we attempt to measure permafrost temperatures and active layer depths. How do we do that? Well, we have a database that is actually not online yet. It's going to be released very, very soon. And through that database, you will be able to access all data sets on permafrost temperature, but I'm also going to show some snippets on the current evolution of permafrost temperature. That's how it looks in the field. On purpose, I took pictures from the mountains that's in Switzerland here, and it's to show you that permafrost is everywhere. It's in vast lowland areas of the Arctic, but also on very steep rock faces in mountains. Very different setups and also very different requirements when it comes to instruments, for instance, that you have to deploy to measure permafrost temperature. Here, these are holes that are shown by those red arrows, and of course next to it you have like a set of meteorological instruments, and then in those holes there are chains that go very deep and measure permafrost temperature. Now I'm going to show you in the Arctic 4 stations that are shown here with those colored circles. The black points show you the extent of the existing network of measuring stations, and you see there are some very large gaps, for instance in Siberia, but even in central Canada here, where permafrost temperature is simply not measured. But we have some places where we can extract those time series, and now we're going to see some from southern Siberia, southern Yakutia in red, Svalbard in yellow, northern Canada, so Alert, which is by far the coldest permafrost we have here in light blue, and then some data from Barrow, which is in northern Alaska, in green. This is how the data looks. You have the permafrost, so the years at the bottom, and then on the left you have the permafrost temperatures. So you see we start with 0 on the top, that's when it becomes unfrozen, and you see that through time the permafrost temperature is increasing, and it's increasing everywhere. Of course, you have some yearly variations that are linked to climate, but these variations should not distract us from the overall signals here, which is permafrost is warming virtually everywhere in the Arctic. That curve is stopping in 2016. We're working on an update now. What I can already tell you is that that warming is ongoing, and that warming is accelerating. This warming of permafrost is also seen in what we call abrupt thaw, and we will talk about it later on during other presentations. It's basically the disruption or the disappearance of permafrost through abrupt processes. There may be mass movements, landslides, or in that case, coastal erosion. This is a stretch of coast located in northern Canada here, and I'm going to give you a glimpse of what these coasts, which are really held together only by the permafrost, are now experiencing in terms of dynamics. Here we have like the rates of erosion at this place, which is 0.4 meters a year between 1955 and 1954. 0.4 meters a year. This is already very substantial for any coast located around the world. This will threaten a lot of buildings that are located at this coast. In those locations, it is very substantial. Between the 1974 and 1996, it doubled to 0.8 meters a year. Then until 2007, the rate of erosion there was 2 meters a year, which is again more than a doubling of the rate of erosion. And now, over the latest period, 2011 to 2022, we jumped to 7.6 meters a year. So a very substantial increase. There are some places that are eroding less fast, of course. I chose a location where like the rates are very substantial, but across the Arctic we have rates of erosion that are now in excess of half a meter a year, closing 1, 2, 3, 4 meters a year at some locations. So it's very, very substantial. And this has impacts. Impacts for buildings, impacts for the cities, for instance, that are located on permafrost. What I'm going to show you now is a figure showing you the way that permafrost temperatures have developed in many cities located on permafrost. You have at the bottom the permafrost temperature, so colder permafrost on the left here, with a minus 10 degrees, and warmer permafrost, or like 0 and above, towards the east, towards the right of the picture. And then I'm going to show you the settlements for which we know they've been cooling, because there are some of them, and the one for which we know there's been warming and the extent of that warming. So this is the cooling. You see like a couple of locations, Ust-Nera, that's in Russia, Kaninga, but Ranking Inlet, which is in Canada, Iqaluit, Magadan, and that's about it. So those are the locations where we've seen some cooling in the Arctic. And, oops, sorry, I pressed the wrong button. And that is the extent of warming. A large range of locations here that have been experiencing substantial warming, some warming exceeding 3 degrees from some locations for permafrost. So very, very warm. And the fact that you see a general trend here toward the bottom and mean that is explained by the fact that as you get closer to 0, the warming generally like slows down, because you need to melt a lot of the ice that is in the ground, and that requires some energy. But basically the warming itself is almost as substantial in terms of heat that is being consumed. It's just that in terms of temperature you see a slightly slowing down here. But like the impacts are just as drastic, because when you approach 0, that's when the soil loses all the strength that it requires to support a lot of the infrastructure that is located on permafrost. Why is it relevant? Because we have a substantial amount of people who live on permafrost. On the left here, you see the amount of people that live on permafrost in the US, in Canada, in Greenland, and then some of the Nordic countries here, and those numbers are not that huge here, and they are not that huge simply because the overwhelming majority of people who live on permafrost are located in Russia. And this is also where most of the economic activity takes place, in Russia. These are projections, and what they are meant to show you here is with compared to the baseline, which is shown in orange, which is the current extent of permafrost, or the one from the 60s to the 90s, what we expect the permafrost extent to be for different warming scenarios, starting with a 1.5 warming here, for which we would have a reduction of the permafrost extent no matter what, and then up to plus 5 degrees here, which is not unheard of when you think of the warming that we see in the Arctic, and then a very strong disappearance of the near surface permafrost. This is important also, and that is on that map here that we show later on again, because those locations are also containing a lot of carbon. What you see in green here, and also in blue under the sea, but look primarily at the green colors, is the amount of carbon that is stored in the soils. And that carbon is likely to be mobilized as we cross the 0 degrees line. Oops, sorry. And that was it. That was the end of the presentation. I hope I provided you with a very quick overview of what the current dynamics are, and now my colleagues are going to dive into the specifics of permafrost warming and the consequences.
Thank you very much, Rick. So I think we can ask Fabian to step up and see if there are any questions for Hugh in the meanwhile while we're shifting. No, okay, so. Okay, so our next speaker is Fabian Seemann from the Alfred Wegener Institute in Potsdam, Germany, who is currently a PhD candidate, but will very soon, I think, be a finished PhD. You are wrapping up your PhD on this topic. And Fabian will tell us an overview talk explaining the current knowledge on the permafrost climate feedback. So please go ahead, Fabian.
Yeah, thank you, Gustav and Hugues, for the introduction and also for this very nice overview talk. So yes, as Gustav introduced me, my name is Fabian Seemann and I'm a PhD candidate at the Alfred Wegener Institute in Potsdam, Germany. So I don't have to talk too much about this slide as Hugues has introduced this to you already. Permafrost is permanently frozen ground that stays at or below 0 degrees for at least 2 consecutive years, and it covers about 22% of the northern landmass. And in addition to that, there's also subsea permafrost, which has an aerial extent of about 2.4 million square kilometers, which compares to the country size of Algeria, which is the 10th largest country in the world. Permafrost in the column space has an extent of 10 to hundreds of meters, and what this means to the carbon dynamics I will explain to you during my presentation. To get a better idea of the Arctic also, I want to mention that that 34% of the world's coastlines are located in the Arctic Ocean, or around the Arctic Ocean. So to explain to you why permafrost is relevant to the climate system, I'm showing you this graph here where you see the land mass distribution along latitudinal transect from the South Pole to the North Pole. Now in this plot you see also the permafrost extent in the northern hemisphere, and adding into this plot now the below ground carbon storage shows this distribution. And right now we are in Bolin in the tropics, just south of the equator, which already holds a substantial amount of carbon in the ground. Now comparing Arctic permafrost, you notice that the permafrost storage here is even more substantial. If we compare this to the atmosphere, for example, we have about twice as much carbon in permafrost compared to the atmosphere. Now we can also look at deeper stocks, reaching down to 17 meters. This adds up even more carbon to this pool. And as I mentioned, there's also subsea permafrost, where we could also plot in the carbon storage here, adding up on this carbon pool. Now, why is this relevant to the Arctic? Thank you. So now why is this relevant to the Arctic? The Arctic is warming 3 to 4 times faster than the global average. The mean Arctic warming is at a rate of about 0.7 degrees per decade since the 1980s, compared to a global mean of about 0.2 degrees per decade. And this leads to this local amplification in the Arctic, which is actually all the way up to about 7 times amplified, such as here in Siberia, north of the coastline. And this warming translates into ground, and into the ground. So permafrost, as a result, is also warming and thawing. Now, when permafrost starts to warm, we see the start of the permafrost carbon cycle, which I want to explain to you with this graph, where you see ground temperature rise, which leads to microbial activity. So basically, microbes eating up the organic matter stored that was formerly stored in permafrost, which degrades the material, producing greenhouse gases such as carbon dioxide, CO2, and CH4, methane. And these greenhouse gases will eventually be released to the atmosphere, contributing to climate change, which again leads back to ground warming and thawing. Now, permafrost thaw manifests generally in 2 different ways, that is gradual thaw and abrupt thaw. And gradual thaw describes the top-down thawing of the soil column. And what I want to stress here in my presentation are abrupt thaw processes, which cover more than 20% of the permafrost region in the Arctic. And I would like to explain to you abrupt thaw with some examples. So abrupt thaw are disturbances that can lead to the formation of thaw lakes, for example. So when the ground ice melts, the ground is subsiding and these thaw lakes, they capture the heat from solar radiation, leading to additional thaw below these lakes, and this is how these lakes grow, and you get this very scattered landscape with this example here from northern Alaska. Another example in hill slope terrain are slumps. You can find them, for example, along rivers or coastal areas, and here I am standing in a slump several meters below the surface level, and this leads to the exposure of ground ice, which leads to increased thawing rate. Now, another process that is associated with abrupt thaw are fires, Arctic wildfires, as they contribute to post-fire thaw of the ground. So one key question in permafrost carbon research is, how does rapid thaw change permafrost carbon dynamics and the remaining emission budget? Here you see a huge slump from northwestern Canada, actually Herschel Island. And with this example, I would like to introduce some methods how we can map the impact from thaw slumps. So generally, to map the Arctic, for mapping the Arctic, we utilize remote sensing techniques with satellite imagery or aerial imageries from flight campaigns. And in this example, we can see multi-year data set, which also utilized AI detection of thaw slumps in the circumarctic region, which now comprises more than 40,000 thaw slumps in a vast area of about 8 million square kilometers. And also here are introduced deep learning techniques and modeling efforts on the multi-year data. Now, on the landscape level, now I'm talking about bottom-up approaches to quantify greenhouse gas fluxes. Chambers can be used to monitor greenhouse gas fluxes of specific landforms. And if we want to look more on the landscape level, eddy covariance towers can be used to get a better picture of the entire landscape. So the permafrost region has turned into a greenhouse gas source. Between the year 2000 and 2020, the region was a net source of methane, CH4, mainly expressed in emissions from non-permafrost wetlands and lakes, these thaw lakes, which I introduced to you earlier. And CO2 was overall near to neutral due to boreal forest uptake, which was outweighed though by boreal fires, which I also introduced before, and emissions from rivers. Now, in this assessment, there are also lateral processes taken into account, which are, for example, coastal erosion or riverine export to the Arctic Ocean. And including these lateral fluxes, the region is a net carbon source of about 0.5 gigatons of CO2 equivalent per year. And to give you an idea of what this means, or where we are here in this range, this is in the range of Germany's annual emissions. So permafrost acts as another industrial nation. Now, looking into the future on projections from 2025, so from today to the year 2100, depending on the mitigation scenario, permafrost releases cumulatively carbon in a range between somewhere of 387 gigatons of carbon CO2 equivalent to 624 gigatons of CO2 equivalent. And in this modeling approach, all these thaw processes, which I introduced to you earlier, gradual thaw, abrupt thaw, combustion from wildfires, and the post-fire thaw are included. And this is key in understanding the carbon dynamics in the Arctic, as including abrupt thaw processes adds up 166 to 258% of carbon emissions. Now, the Arctic overall is a carbon sink. So if we include also the Arctic Ocean in it entirely. This is caused by oceanic CO2 uptake and burial in shelf areas. And with climate change, the sink capacity is likely to strengthen due to Arctic greening and carbon burial. However, the sink will likely weaken due to increased soil respiration, so greenhouse gas release, which I introduced earlier, and inland water emissions from thaw lakes, as well as we have coastal erosion, which we heard in the previous talk, leading to additional input of carbon into the Arctic Ocean, which lowers the natural capacity of the Arctic Ocean to take up atmospheric CO2. Then we have additional riverine input and near-shown carbon turnover in warming waters of the Arctic Ocean. However, we have also, we call them known unknowns, and this, in this example, I would like to mention some permafrost and processes. These are factors and processes which are relevant for the carbon budget from permafrost. However, they are not sufficiently yet accounted for. So in saline permafrost, which is found in Arctic lowlands and along coastal regions, we have saline deposits from times when sea levels were higher compared to today. And in these sediments, the thawing point is depressed due to the salt concentration. So permafrost might already thaw out at minus 1.5 degrees, for example, and not at 0 degrees. And this leads to earlier than anticipated landscape changes and production. As a second factor, I like to mention subsea permafrost and gas hydrates. Subsea permafrost has a substantial carbon pool, which is generally of low reactivity. Sorry, I don't really know what's going on here. I hope it's better now. So, in this plot to the down right, you see the water column, and below that the subsea permafrost domain. And below that, in parts of the Arctic shelves, gas hydrates are situated. And this is basically frozen methane, which is stable under high pressure and low temperatures. But as subsea permafrost thaws out, there's a risk of a release from these gas hydrates, additional summing up or contributing to carbon emissions from the Arctic. So the key messages I like to convey are that the permafrost region has shifted to a net carbon source. And this carbon sink capacity of the Arctic is likely to weaken. However, there are also unaccounted processes which might exacerbate the permafrost climate feedback. And as a last point, I would like to mention that permafrost carbon emissions will likely continue even if we reach net zero or negative emissions, because permafrost needs time to refreeze and lock in this carbon again. So yeah, thank you very much for your attendance. If you have any questions, we can have them now or later.
Okay, thank you very much, Fabian. So I guess while we're shifting over to the next speaker, we'll see if there are any quick questions. If not, I will hand over to our last speaker of the session. So this is Frank Mark, the European Space Agency. Permafrost from space.
Well, good afternoon. You heard from my two previous speakers already very much detail about permafrost. I will give you more a pan-Arctic overview of permafrost, things what we can observe from space and means how to observe permafrost from space, noting that permafrost itself cannot be observed, but there are a lot of indicators which then help to establish better knowledge of permafrost. I'm coming from ESA's, from the European Space Agency, from our Earth Observation Center in Frascati, south of Rome. And I'm giving this talk on behalf of the overall CCI Permafrost Consortium. Well, let's talk first about ESA and its space missions. We're having 3 dedicated lines of space missions: the scientific missions, the so-called Earth Explorers, related to the cryosphere. Cryosat was our first Earth Explorer. Then meteorology since the 70s, which we are building in respect to EUMETSAT, and in the middle with the European Commission, our Copernicus satellite. And I will concentrate here on the Copernicus satellites. You see it is a family of satellites from radar vision over high optical towards medium optical, and then towards atmosphere and altimeter. Related to permafrost, I would especially put the attention towards Sentinel-1, 2, and 3. And we are evolving, as they are all in orbit and providing since the last decade already very frequent measurements. You will see later on application of these of the satellite. We are evolving as well the Copernicus space component with 6 new missions related to CO2, land surface temperature, CHIME, ROSE-L, CMER, and CRYSTAL. Specifically, land surface, the land surface temperature mission, a high resolution temperature mission, will be relevant for permafrost. Then ROSE-L related to subsidence in permafrost area, that's the radar mission, and the radiometer and the CMER and CRYSTAL will be more for the overall cryosphere. We are as well evolving our existing Sentinels 1, 2, 3 with enhanced observation capabilities. What we are doing with it? We are taking the pulse of our planet. And what you see here are measurements taken from the satellite, converted towards information about the ocean, the atmosphere, land, and the cryosphere. We heard it already from you that these are that GCOS has developed essential climate variables in all these 4 domains. Overall, 55 ECVs, and out of space we can monitor about half of it. And here again you see the cryospheric ECVs. Permafrost is one of those. So now coming more to deriving information out of the satellite and satellite images. What we are using is long and dense time series. Time series of the surface temperature, time series related to the land cover, on the snow coverage, snow depths, and site-specific knowledge related to snow properties. We are combining these measurements in a model in an equilibrium model of energy, and out of this we can then derive the field temperature of the permafrost area. What you see here is the subsurface temperature change at 2 meter in 1997, so almost 30 years ago, and derive from that the different type of permafrost: continuous permafrost, discontinuous, sporadic, and isolated permafrost. In the middle you see as well the yearly minimum of the sea ice level in this area. About 22 years later, you see how, and I'm flipping between the two. Oh, that was too much. You see how permafrost has the continuous has shrunk and discontinuous moved further to the north. Sorry. So we see with these images over time how permafrost on a global scale here from the in a polar view over the North Pole is changing. Now, what do we do within the CCI Permafrost project? We are developing services towards the community. One is a gridded data set based on mean annual ground temperature at selected depths. I showed you before the temperature at 2 meter. Then we are linking that to sea ice. Then we are using permafrost extents derived from the mean annual temperature, and here you see that over the last 30 years we lost more than 1 million square kilometer permafrost in time. Then we have data sets of the active layer thickness. And here you see a correlation of the Arctic impact indices with the observations of the changes in glaciers. So cryosphere in itself is very much connected. Then, oops. Okay, and let's see if the video is starting. There's something. And here an animation over the last almost 30 years with the permafrost mean annual ground temperature at 2 meters, and you see that it is raising from the mean annual temperature is rising from -2 to a little bit above 1 degree. That means within the 3 decades more than 1 degree of, let's do it another time, 1 degree of warming of the mean annual ground temperature. And with this overview of the information, what you can get on permafrost, as indicating areas where more attention has to be taken, I say, obrigado, thanks for your attention.
Thank you very much. So this was actually the last talk we had in this session. We have another session starting in roughly 2 hours where we will dive more into the carbon cycle, the climate feedbacks from the permafrost, how this affects climate, and also how it affects local populations. So So please join us again in roughly 2 hours here in the Cryosphere Pavilion. Thank you.